So hello. So the next speaker will be Kjell Kochale, and I'm very proud because Kjell is working in my department. We know each other since I think 8 years, and it's very interesting. You should know he is someone with a background of instrumental analytical chemistry, and during his PhD, he was very interested also to explore the field of flexible low-code, no-code automation. And therefore, his title is Democratizing Lab Automation. And really keep in mind, he's someone who is no IT specialist, no programmer. So just enjoy the talk. Kjell, the stage is yours.
Yeah, thank you, Thorsten, for this very kind introduction. Good afternoon from my side to everyone here. So as Thorsten already mentioned, I will talk about the democratizing lab automation approach with accessible robotics. And this is a real hot topic because that's the reason why you are listening to this talk. But also the statistics says that this is a hot topic. So in the German Industry Association, Spectaris publishes a report on a regular basis on the forecasted annual growth rate of selected areas in the laboratory. And here we can see from 2019, the area with the lowest expected forecasted annual growth rate was the laboratory automation, still with 5%, but relative less, it was the lowest one. But in 2022, this already changed dramatically. So the lab automation now has a forecasted annual growth rate of 8.1%. And additionally, the new category of laboratory robotics with 6.7% was added. So we have now two categories, with one being the third highest. And then in 2024, the actual newest report was published. And here we observed a shift. The laboratory automation lost a little bit of its relevance, down to 6.6% forecasted annual growth rate. But interestingly, the laboratory robotics gained a lot of interest, to forecasted annual growth rate of more than 10%, making it the third highest growth market for the laboratory. But that is, of course, makes sense because lab automation has a lot of advantages. So we have increased efficiency with an improved accuracy for the working results. We have lower costs on the long term. We have easier traceability and audit trail implementation options. And of course, we have also lower occupational health risk for the employees. But with the conventional automation approaches, there are also some disadvantages. So we always have the high short-term costs due to the acquisition of all the instruments and buying all the stuffs. We have possible vendor dependency. If we, for example, or if we make it with one system integrator and then acquire all instruments from him, then we are definitely dependent on him. We have an increased risk of downtime if one part of the system fails, everything stands still, and everything is dedicated to the one task that was planned to be automated. But that's where the approach of flexible laboratory automation is of interest. The basic concept here is that the adoption and modification can be done by all laboratory domain experts, coming from the normal lab technician over the researcher up to the lab head. This is enabled by a modular design of the laboratory automation station. So every station can be exchanged easily, and every part is exchangeable. Additionally, everything that needs to be programmed should be programmable without in-depth programming language knowledge. So be it the workflow orchestration or the programming of the cobot, everything should be programmable without any in-depth knowledge. The advantage here is that the laboratory staff itself can change their process and can adapt it to their needs. So, for example, if they need more functionalities, they can do it by themselves. They can set up new processes by themselves. If there is any problem, they can easily exchange parts of the automation setup. They can reuse equipment for new automation setups, which we will also see later in a use case where this was done. And because of this open architecture, the vendor login is dramatically reduced. Of course, there are also some disadvantages. So we still have the higher investment costs. I would say it is comparable to the normal automation with a system integrator, maybe even a little bit cheaper. Additionally, we also have disadvantages with the increasing training that is, of course, necessary. So the laboratory staff needs to be trained for the workflow orchestration software, for the cobot programming, and so on. So that will definitely need some additional effort. And I think the biggest bottleneck is the additional effort that is required for certification. So especially the CE certification in the industrial area and for the regulatory compliance, especially with ISO certification. So right now, I would say there are a few obstacles for widespread implementation of the flexible laboratory automation. So the first one is that we are all, or that our approach is that the experts in the laboratory work should automate, making them really good for the workflow knowledge. But of course, they have little to no programming knowledge. So everything needs to be done without programming knowledge, or with really basic one that maybe can be done by ChatGPT, but with no in-depth knowledge skills. We are also not engineers, so we don't want to automate or generate our own automation stations. So everything should be off the shelf. The laboratory equipment should be used when possible, because normally you are familiar when using it, and that makes it more easier to implement. And cobot probing should also not be done with in-depth programming skills, but rather with easy user interfaces. And that's where the democratizing approach comes in. So I will show some approaches on realizing the workflow orchestration and the cobot programming without any programming knowledges. We will retain the legacy devices in one use case. So we used an old 10-year-old pH meter that was easily integratable, and everything else was normally realized via standard interfaces. So the aim here is clearly that all employees should create their own workflows uh, yeah, um, um, without a lot of external help, I would say. Coming to this, I will show 3 different use cases how we approach this flexible automation approach. The first one is a small sample preparation workflow for an effect-based assay. This effect-based assay is for the detection of neurotoxic substances by an acetylcholine esterase assay with a lot of different stations. But before I come to the workflow orchestration, I will briefly explain the cobot programming, because this basically stays the same for all the workflows that I will show here. So cobot programming is actually not that big hurdle anymore. Normally, we use some third-party software, but also the teach panels from the cobot manufacturers offer similar functionalities. So they normally have predefined building blocks for like moving or gripping tasks and so on. And these tasks need to be parameterized either in silico or directly on the cobot. And then these building blocks are connected to one workflow. And sometimes it is possible to also simulate the process. And for this, we can upload CAD files to prevent collision with the environment, for example. So that makes this cobot programming also very easy and very straightforward. And I would say that is basically what a good way to be solved. The more difficult part is the workflow orchestration, and that's the reason why I will focus on this in the next in these 3 use cases. For our first one, we used a programmable logic controller, but to be honest, we started with just the cobot controller, but we came to a limit here and then switched to the PLC, because it has more interfacing options. A PLC is an industrial computer for the process control, for machine control, and I think it's most prominent from the automotive industry. The advantage of PLCs is that they are modular expandable, so they basically always consist of this central CPU and an additional power supply for powering the CPU and the other modules, and everything else can be added as necessary. So, for example, we have digital input and output modules. We have a router for the connection, for example, of Profinet devices. We have a Wi-Fi module in this case for external access, so it can really be adopted to the individual needs. And the good thing for PLCs is that they have a huge or huge options, many options for the interfacing opportunities. So we can, yeah, have basically no limitations as these systems are designed to be open. To realize this automation approach, we basically set it up this whole automation workspace that we will see in the video in a few slides. Then all the basic external stations were connected via 24-volt input-output signals. Um, then we added the cobot and the human machine interface via Profinet and via Ethernet connection. And then we implemented the software workflow, then the human machine interface configuration, and then we could start with the complete workflow. And I think a lot here are skeptical on PLC programming because that is definitely one thing no one learns in chemical studying. So I will show how easy that actually is. Basically, we just need two programming languages. The first one is the sequential function chart. That basically works like a workflow from the top down to the bottom and consists of two main building blocks. On the one hand, it is steps. There are these gray boxes here. Steps execute tasks. So, for example, they control outputs or they control the cobot movements. And the other important part are here these transitions. There are these vertical black bars. And these transitions are the condition to switch to the next step. So they can be, for example, an input signal or a finished cobot program. So the next step is executed. And then we basically just have these parallel steps. So it's basically just um, yeah, fulfilling or doing two or multiple steps in parallel, or these alternative branches. That is basically depending on the input conditions. Another step is executed, and that's all the background for the sequential function chart. To control a little bit more in-depth devices or in-depth allow a little bit more in-depth control, we also need this function block diagram, but also these blocks can be easily added via drag and drop from the library within the PLC. So we drag and drop it here, and I think it's pretty clear how this building block is structured. So on the left side we have the input, and on the right side we have the output. And I think it's pretty clear that this execute input is when it is when it's set it true, then this building block is executed. And I think it's also pretty clear that as long as this building block is executed, this output here busy is true. And that is the thing that we can perfectly utilize to control this sequential function chart workflow, because as we now use databases that look somehow like Excel spreadsheets, we can define variables. And these variables can be reused throughout the whole project. So for example, we have now here the variable which is true when this movement is fulfilled. And we can reuse this variable also in the transition condition of the function chart. So that when the movement is fulfilled, the transition condition gets true and the next step is executed. The nice part here is that these variables can also be directly reused within a human machine interface. So it can be basically be drag and dropped in this user interface and can then be deployed directly on a PC for a human machine interface or on these special panels, making it really easy later to interact with the machine. And here we can see the setup consisting of different stations. I don't want to show the whole video because that will take too much time, but just a quick overview. And here we can see the PLC in the dark with the LEDs indicating when an external output is controlled. And for example, here on the laptop, you can see the human machine interface for the interaction with the machine and for the status information. For example, as you can see, this linear rail is also a function block diagram where we put the millimeter movement range as an input in this function block diagram. The advantage using this automation approach is that it's relying on a highly established industrial standard that allows a lot of fault conditions. It's made for automation basically, so it's really established for these setups. Also, it allows an easy integration of human machine interfaces, so the control can be realized pretty easy. Um, It also offers some industrial interfaces like OPC-UA, and the interesting part here for the laboratory at least is that it's compatible to Let's OPC-UA, so Let's is the companion specification for the laboratory. The disadvantage, on the other hand, is of course that this comes from the industry, so it has no compatibility with the laboratory. So we don't have, for example, audit trail implementation. We have difficult integration of laboratory devices, for example. Additionally, if we want to connect external stations, we normally need uh, electricians to connect these stations, and of course to learn this programming language in the tier portal, for example. So for the programming of the PLC, we need some expertise or some time for training the stuff. Coming directly from the other direction is the next use case. So here we have a small, simple preparation um, workflow for our water analysis part, where we take our pH value. And the interesting part here is that we control this workflow with our laboratory execution system. So this is more easily integrated with the existing laboratory devices, but of course it's less made for the automation approach. But let's start with the requirements for this workflow. So we have a water analysis laboratory here, and they need to take some basic parameters before they do the advanced measuring stuff like HPLC-MS measurements. And for this, we have a pH meter, but the problem is it takes some time until the pH value is equilibrated. Additionally, there is always the risk of sample mix-up. If we have a lot of sample in one row, then it can always happen that there is some mix-up, and we have then later issues for the actual analysis part. And of course, we also have limited traceability, as we still need to read the value from the screen of the device and track it manually, normally on a paper-based workflow. And that's where the automation steps in. So as I already said, the process is controlled by our laboratory execution system lab operator. The sample handling is fulfilled by our cobot, which was reused from the previous setup. The pH measurement was done with a legacy device, which is, I think, between 5 and 10 years old and just has serial communication. And because it is done with our LES, we also have easy integration in our sample database, which allows the easy integration of the pH value into the sample database. The to-do for realizing this workflow was actually to dismantle the old setup because we wanted to recycle as much as possible, set up the new workspace, so basically just the one station with one storage position and the cobot. Then we needed to program all the cobot movements, connect the PLC and the cobot, because the PLC was used for the connection to our LES. And also the pH meter needed to be connected to the LES via a middleware system. And basically that was all. So the challenge here was that we had a kickoff at the end of last year, and 1 month later we had a workshop where we wanted to present this work. 4 weeks, I think, is pretty much time, so I was really relaxed. But from the 20 days remaining, I was 2 weeks on a conference. Then there were a few public holidays, and I also needed to write a final report for the project. So from the 20 days that were originally remaining, only 8 days were remaining with just partial time. So uh, we don't have that much time. But that was no problem, because as we can see, um, it took 1 day to realize, set up the connection. Then there was a public holiday. Then we could program the cobot movement and realize the PLC connection. Then on 1 day, I needed to make some debugging because I made a mistake with the connection. And on the basically last day of the implementation, I could transfer these all the necessary data to our laboratory execution system, which basically enabled the workflow control. For the programming of the lab operator workflow, we relied on our external partner who wrote this program for us. So it was not completely possible without any programming knowledge, but basically we didn't need to program a normal program, but we need to write configuration files. And these configuration files are written in either YAML or JSON and are on a pretty high level. So for example, in this picture, we can see this controls one cobot movement, this controls the other cobot movement, and this executed the pH measurement. So as you can see, it's really clearly written what needed to be done. So it makes it easier for lab staff after a little bit training to generate these workflows, even if some programming knowledge is necessary. Here we can see this small setup, just a small pick and place setup um, with these blue boxes that appear on the screen. The software or the lab operator shows that the this step is traced, so everything is also added in our audit trail, um, which makes it easier for the certification later. And we can now see that the pH measurement is fulfilled and that there is a value that is written in the database. So it was pretty straightforward to fulfill this task, even though, of course, it's not a very complicated one, but nevertheless, it makes work easier in the future. The advantage of this concept is that this comes from the laboratory part. So it's easy to integrate laboratory devices, um, either directly or through middleware. It is way easier to allow the integration of audit trail and to achieve the certification for this workflow. It's also easy to have the integration into the LIMS or ELN system, so making it even more interesting for industry, for example. On the other hand, we have, of course, a disadvantage that some programming skills are necessary. Additionally, these LES normally are made for digital workflows and not for actual automation processes. So they are pretty linear. There is not that much error handling or that much if-else conditions. So they are more for straightforward process controls, making it not that feasible for complex automation platforms. And depending on the software you use, you also have ongoing licenses costs, depending, for example, on the amount of devices that are integrated. The last small use case is one approach I came across just, I think, 2 or 3 months ago, and that is the use of no-code automation platform. It's not directly a use case with a specific background, but more a conceptualization or showcasing of the option that we use. So I came across this Node-RED platform, which is an IoT open source free of charge platform. And because it's open source and community driven, it already allows a lot of different integration options, which is normally done by community provided contribution platforms or contribs. The basic concept here is that Node-RED consists of different nodes. These nodes can be, for example, inputs or outputs, or special functions for processing data streams. Basically, we have here these nodes that are drag and dropped on the user interface and are then connected via drag and drop to one workflow. Um, and we basically just need to parameterize these blocks, which are still on a high level. So every data processing is automatically done in the background within these nodes, and user basically don't need to interact there in any way. Another advantage is that it really allows easy dashboard integration. So there are special libraries for these dashboards. We can directly integrate nodes for the dashboard in the workflow and this is directly displayed on the user interface. So for example, you can see this button node over here, which is basically this bottom here in the user interface, where I just changed, for example, the color and the symbol, but nothing else. So it's very straightforward for integration. The advantage is it is part of the Internet of Things, this Node-RED approach. So it already allows a lot of interfacing options. So for example, serial communication, MQTT, OPC UA, and so on can be easily integrated via dedicated libraries. But additionally, it allows some in-depth control of selected devices depending on the libraries that exists. So for example, in our case, I know that there is a universal robot license. That's the one I showcase here later in the use case. And there is also one library for the S7 PLC from Siemens that we are using, and they allow more in-depth control, and they also allow easier integration. So yeah, here are some interesting concepts for this small demonstration. We used the UR robot contribution and the dashboard um, contribution. And here we can see how one workflow may be structured. So for example, this IP address is one node that is directly implemented in the basic functionality of Node-RED. Then we have one function to limit the amount of messages to 1 per second, because otherwise it will be way too much. Then we have this special function of the interfacing for the cobot. That, for example, is one node that is generated through this UR robot contribution. Then we have some functions to filter for the interesting parameters that we want to show. And then the showcasing is done with these special dashboard nodes. And that is basically all. The configuration is really high level. So for example, for this UR robot, we just needed to add the IP address and the port, and everything else was done in the background. So I don't need to program anything here. And that made the setup pretty straightforward. So we just needed a Raspberry Pi, install it with Node-RED, connect the stations via IP address normally, and then we could directly start with the workflow. And here we can see this setup. So again, it's just showcasing of the use of the dashboard for the cobot. So I select, for example, a method now in the drop-down menu. Then I executed it via play. Then I used another method or load another method that normally is continuously done. But in this case, I pause it, and a few seconds later, I resume it with a play button. Then I can, for example, ask of different status parameters that are displayed over here. And then, for example, I can emergency stop it, and you can see in the LED indicators here in this case that the emergency stop is activated. And here on the right, for example, you also have the visualization of some status parameters, for example, the temperature of the cobot joints or of the velocity of the cobot joints. And that was really straightforward, implemented in basically one day, including the setup of the Raspberry Pi. The advantage of this approach is that it's a really low level starting point. It allows easy drag and drop workflow programming without any knowledge. The setup is really straightforward, and there is a lot of help because it's an open source approach. So the community is normally helping a lot. And the other advantage is that because it's an open source approach, ChatGPT has a lot of knowledge on it, so it can also support very well in this regard. Of course, the disadvantage is it is not made for the laboratories, so there are no libraries for laboratory device integration. It is an open source solution, so there is no company behind it that can help in cases of trouble. And of course, you're fully dependent on the work that uh, one else did. So if there is any error or if the library is not supported anymore, then you are set on your own. So that's definitely a disadvantage for this approach. But nevertheless, it's really a low-cost approach, especially interesting if you want to start with this easy workflow orchestration. Coming slowly to the end, I will start with some bottlenecks on these that are still there for the flexible automation. So there's basically no universal solution for workflow orchestration, especially with the focus on the laboratories. So it's still difficult to integrate laboratory devices. And there are only a few solutions that include, for example, audit trail or make the CE certification easy, which is still a huge barrier, especially in industry. But there is a perspective that this will become better in the future. So with the increasing prevalence of open standards in the laboratory environment, for example, CELA 2 or Let's OPC I would expect that the device integration will become much easier. And with this also the emerge of workflow orchestration platforms will be more prominent, I would say, because when devices can be easily integrated, this part is taken from the software developers of these software orchestration, workflow orchestration platforms, which will make it, more prominent in the future, I would say. Robot prompting is already pretty easy, I would say, but there are still some new approaches using, for example, prompt control or voice control for the programming of the cobot, making it even easier for in the future to program the cobot movements. And last but not least, I would expect that with the support of artificial intelligence, these CE certifications, for example, or these certification processes will become easier because you basically just let the AI check your whole workflow and your components that are implemented. It will already start with the necessary documentation and probably also suggest some improvements that are necessary to receive the CE certification. And with this, I hope I could show you the increasing relevance of the laboratory automation, especially of cobot-based laboratory automation, some requirements for the more widespread adoption of flexible automation, especially with the focus on easy workflow orchestration um, without any in-depth programming knowledge. I showed some different use cases with different approaches for this workflow orchestration with their own unique advantages and disadvantages. And I gave a small perspective on the future of the flexible laboratory automation. So it will be really exciting in the future. And with this, I want to thank you for your attention. Looking forward to your questions and some self-advertising for our own analytic talk with the special focus on laboratory automation and digitalization. Thank you.
Ja, perfekt. Danke, Kjell.